Okay, so I hope you enjoy the exam. Sorry, you don't like paper-based exam. Oh, I yeah, I can see that. I haven't write for a long time. Actually, I just type things in. So, quick recap on what is a computer. Basically, you have a processor that perform any data processing, right? And the data come from the memory, which come from your I/O, like your keyboard, monitor, disk, files in your system, right? And now what we need to develop further is we need to know when you want to control your machine, right? Or your computer, if you will. The instruction set architecture is the definition of the list of commands that you can issue to a computer. Now, we show earlier in the semester, say, hey, for whatever program you're programming in, Python, Java, C, C++, Rust, Scala, or whatever program you want to do. When you have that program and you compile them, right, the output of that is basically binary file. The binary file are compiled for a certain ISA. Out of curiosity, have anyone heard about this x86 ISA? These are what used in AMD and Intel processor. How about the ARM ISA? Good. Yeah, so ARM ISA is used in a lot in mobile phone. Also the M1 and M2 chip from the MacBook. Think of it as the language that control the hardware. These are the list of the reason why we call it ISA is because these ARM and x86. And if you will, things like RISC-V ISA, there's another emerging ISA that's getting more and more dominant as well. These are just the list of commands we can issue to the hardware. So the way, basically, if you think about it, I would explain it this way. When you want to design a piece of hardware, you would first need to figure out, okay, for this hardware, will it be run in what ISA? Is it x86 or is it ARM? Then you look at all the instructions, and basically you build the hardware that can run all those commands, right? Which means that you have the program, right? Which get compiled into the binary for each ISA. Now you have the binary that follow the command that say, hey, this program that do A plus B. It's just a command that say, take A from here, take B from here, add them together, write the result here. So those are the commands. Then the computer can do the job and run your program. All right. Now, sometimes you might see this word as well called microarchitecture. Microarchitecture is basically the design of the hardware that implement the ISA. It's the design that would implement how do I actually finish the command given the ISA. What are the circuitry elements that I have to put together to run the command? All right. So your microprocessor that you buy, your Intel and AMD and Mac M1, M2 CPU, they are basically ISA and microarchitecture. It's the interface between the software and the circuits, right? That means that you don't have to talk in 1 and 0 anymore. You just need to talk in assembly. Okay. How many people want to talk in assembly? Good. No one should. All right. No one should want to do that. That's why we have the compiler, right? So let's assume because we are programmer, we have to talk in some programming language like Python and C. Now that we have the compiler, it will compile to binary, which is basically assembly, which means you can run. All right. So let's get sidetrack a little bit and talk about this thing called semantic gap. Semantic, the way I would compare and define the word semantic is meaning. Think of it as, let's say you write an English essay, right? What's important about writing an essay? What do you care about when you write something? Let's say you have English assignment, yes. The structure, what else? Grammar, what else? Story. You need to have some story that pair to the structure. Then when you write it, you have to follow some grammatical rules, right? What does grammar tells you? It basically allows you to understand things in the exact way, right? Let's say, if I say, I have a cat, I have as a plural verb, a cat, right? It means that, how many cats do I have? One cat. What if I say, I have a cat with the S at the end? What would happen? Confusion, right? Do I have one cat or do I have multiple cats? Because I do not follow the rule, the grammar. The English grammar would dictate that if I have one cat, I have to say a cat. If I have more than one cat, I have cats. I have multiple cats, for example, right? So that's why I would compare grammar with syntax. How many of you got syntax error when you were working on assignments? Everyone. Why is that useful? Syntax error happens when the computer are not sure what do you mean, right? How many people want the AI to kill all of us because it doesn't really understand what are we trying to mean to them, right? So you better follow correct syntax to know and command the computer the exact thing you want to do. That's why when things are ambiguous, you get syntax error because the computer say, hey, I should not assume this is what you mean. Please rewrite your program. Semantics are the information that go with the meaning. What is your program trying to do? So that's semantics. Semantic gap is the gap between your software and the ISA. In other words, in human, a little bit more human language, how far is your software from assembly? This is basically have to do with the assembly language design, because you have to come up with what should I do to design my assembly language, right? I can have the language with a large semantic gap. Assembly just control voltage, for example, right? I mean, it would work, it would run. Then your compiler or your compiler friend will murder you. If I have the program, how do I just control each knob in my computer? Yeah, that's too much. All right, that's big semantic gaps. The compiler basically have to generate the instruction to control your computer. Small semantic gap means that your ISA looks like a high-level language, like C or Python, right? Your assembly language will reflect, have similarity to like C or Python. It might have even things like support for array, support for struct, support for operation for each array, a support for a set operation, for example, right? This allows more application specific hardware optimization, but it's also quite bad in the sense if it's too small. If it's too small, then the compiler job is like just translate. That's all. Not a lot of room to automate and optimize. Most optimization in that case becomes like hardware optimization. And when you have two ISA or two assembly language that they have to talk, for example, you have a program compile for like Microsoft Word compile for x86, your Intel and AMD chip, and you want to run it on an M1 or M2 chip, you then have to translate, change the semantic gap. This can be done in both either in hardware or in software. Right? That said, I say think of it as like a normal human language. You don't want a lot of those, right? I can look, for example, Which language is more useful, Thai versus English? Just be honest. Yeah, you can likely talk and communicate with more people, right? With English. So computer cannot understand or execute a program compiled from a different language. Even if you have a previous version of ISA that are not compatible with the current version, then your program will stop to run. What you have to do as a programmer is means you have to have the source code recompile for a new ISA. Why is this annoying? Yeah, let's say you run a software company, right? And you have to have the client installing your program. And let's say the client say bought your software, then 5 years later, their hardware is too old, they buy a new computer. It happened as a change. What do you have to do for your client? Am I gonna go to that version, recompile for the new hardware? That's annoying, right? That's why backward compatibility is quite important when it comes to hardware design, because you want to make sure old program that's been compiled a long time ago should still work now. So that I don't have to go to the software company and recompile it again, right? There are quite a lot of programs used by like human space programs that are compiled in things like COBOL, which is like ancient like language that now changed to like C, C++, Python, Java, right? If parts that are if program compile back with that language go wrong, right? You probably then how many people know how to program in Fortran? Neither am I. Let's say you have that old language like Fortran or like COBOL, right? These are super old language. And let's say I have parts on the space already or in a spaceship, right? That is written in that language. And that's a bug because you introduce the new parts to the spaceship. What do? You go back, find whoever write that piece of code, right? That piece of code maybe is written in the 70s. How old is that person? Is that person still alive? Right? That's a big problem. So to maintain this kind of software is hard. To maintain it's hard, right? So that's why people actually retire software after some time. Hardware is the same thing. You also retires ISA, retires hardware. But the key issue is if you have a new ISA, it means that the whole pipeline, the compiler, the program has to be re-optimized for the new hardware with the new ISA. Alternative solutions what Apple used in Rosetta with like how many people use Rosetta in the Apple MacBook? The M1 and M2 chip. Basically, this is a piece of software that allows you to run the program not designed for an ARM assembly. Let's say you have a program that only works in the AMD and Intel chip using x86. You can run it using Rosetta to run that program. Right? That's what we call code transformation, transform your code from one ISA to another. The conclusion is similar to human language. You don't want a lot of those because the more languages you have, the more overhead for us to maintain all the programs and all the hardware. It's better to have one good ISA or 2 or 3 good ISAs and that's all. Maybe how do we have multiple? Okay, great question. Back in the day when we are not down to like these are the ISA that we want, there was a debate between should the ISA be simple, for example, just to add, multiply, division, and then let the program do the rest. I optimize in the algorithm, in the compiler, and make sure I compile into a really, really nice, just a few commands of assembly. Another chain of thought is like, for example, the x86 school of thought, which is, hey, but in that case, what if I have the hardware that can do fancy things like a loop? I can have a hardware that runs a loop. and do like count up for every loop iteration. For example, maybe I want the instruction for that, right? So maybe I want more instruction to do fancy things. So people debate, and to be honest, there's no winner for me. So there are the sides that start with like ISA can be complex, and I have this thing as x86 that do a lot of fancy instruction, can do a lot of fancy things. I can write a program, I can write the hardware to do these fancy things. And then there's like this thing from like RISC-V, for example, or MIPS. MIPS is used in PlayStation 1 and PlayStation 2, which come from school, the school of thought is like, hey, the language should be simple. The rest can be done through the software. Compiler, do the job. Programmer, do that job, right? Then the hardware, because it doesn't have to implement every command, I have spare parts to do something else. So this simpler ISA is really, really good for example, mobile phone. Because I don't have a lot of space for my chip, right? It means that maybe I want to design an ISA that only do certain limited amount of things. And then the rest, I would use the rest of the space here for some other component. So ARM, for example, is like a really, really good example of the ISA that is optimized for power and simplicity compared to x86. Then x86 was a good example of things like the ISA that goes well with, say, data center and server. Again, to be honest, things change all the time. So the same logic nowadays, it's kind of different now. Because you see, Apple took ARM ISA, which originally is good in mobile, use it for their laptop. Why is that the case? Apple redesigned quite a lot of components to make it really powerful. It performed really well compared to x86, but ended up being a lot more power efficient. I've heard people that get a MacBook and can have the laptop open for like 8 to 10 hours. Imagine this laptop that run for like 10 hours, right? Probably won't never see it happen. So that's the trade-off. But again, things get a little bit more complicated in terms of what's the de facto, the best ISA when you have power, when you have performance into the mix. Now, the next follow-up question is what goes into the ISA? So I would compare this to normal human language, right? When you want to ask someone to do something for you, I was about to say, when you want to send a command, which is basically ask someone to do something for you, what do? You talk, right? You tell the request to your recipient what should be in the request. Subject, verb, object, right? What am I trying to do? The verb, and then the subject and the object of my sentence. Same logic with ISA. I want to do, say, A plus B. What is the verb? The addition with the verb, right? And then A and B becomes the subject or the object, you will, right? So the technical term is you have the opcode. Opcode is the verb. What am I doing? And then you have addressing mode. The data type, is it integer? Is it floating point? Addressing mode is how do I go to the address? What is the mode at which I work with the address? Instruction type, is it compute? Is it memory? Memory means that I want to get something from memory. I want to get my data. I want to load my data. I want to store my data back to the memory. It can be control flow. Control flow means that even have if else, right? If this, else that. It means that if it's true, I run this part. If it's false, I run this part. That's why we call it control flow, because we use the word control to determine the sequence of instruction that the program runs. Most of the time, how does your program run? How many people think it's line by line? from top to bottom. That's the typical sense, right? Unless you have what? When you skip a line, if else, for loop. Yeah, that's why we have control flow. It flows differently from top to bottom. Now it flows, oh, jump here, right? That's why we call control flow. So that's the third instruction type. In most, if not all ISA, those are the three types you're dealing with. The one that dictates what am I doing with the data, the one that dictates how do I get the data, the one that dictates how do I run the program. That's all. When you have these three types, you have a functioning computer. That's it. All right. Now, if you abstract away, thought, if I can implement addition, subtraction, the way to get to DRAM and the way to handle loop and if else, I can run my program, right? And that's it. The third thing is register and condition code. How many people program with a temp variable in your function? Everyone. I do too, right? In I, in J, in counter, that's the register. Register are, think of it as the unit that you can store data in inside your CPU. It's really fast. You can use it for any purpose. Condition code has to do with when I run an instruction, was my previous instruction result in a carry? Was it result in an overflow? Right? Remember your question earlier from when you talk about data size and all those things, right? What if you add two numbers and it overflow? Condition code will be updated with that, with what happened to previously. So now your hardware knows what happened to my program. Now, the next thing is you have to interface with the memory. If you think about it, modern computer, memory is at the heart of everything. It connects your I/O, your keyboard, your monitor, your disk, your data, where the files are, your program. It's all going to be put in the memory when you run your program. So it's the processor is your brain. The disk peripheral is like your sense, right? That you can touch, you can smell, you can eat things. The memory is kind of like the entity that connects everything. So you need a way to figure out the address space. Is this owned by the kernel? Is it owned by the user? Who owns this part of the memory? How many people got tech thoughts already in your program? That's a feature, not a bug. All right. Because segfault happen from when you're trying to access some illegal location in your memory. So it's better rest a segfault than letting your program run. Because it can be super dangerous if you let program run. Windows can crash, for example. The ISA will have the way to determine if there's any violation happening. Addressability, should I be able to go to the exact bit or the exact byte? Or maybe I don't need to go to exact byte, just get 4 bytes at a time in chunks, right? Let's say I never have to do data as a character, it's just integer. Then why do I even have to access each individual byte, right? Just so 4 bytes at a time. Alignment, which has to do with where things are aligned when you use pointer. And the virtual memory management, which basically we're not talking about that, the last bullet point right now. That's toward the end of this semester. So what else for completeness? You have things like, what if you have interrupts? For example, if you want to, how many people have the task manager open and you do end process when things hang? Basically what happened when you click end process, you send an interrupt called MUIC-Syskill to kill this dying process that eats up your memory or your CPU. The ISA have a definition of when this happens, what's supposed to be the behavior? How do you handle X and Y and Z? It would tell you how to handle things. The access control, how do you control the access by system, by the user, by the OS? the priority, how do you set the priority, which can then be used by the OS. If I have to, like, let's say you run 5 programs and you only have 2 core, 2 CPU, 5 programs. At any given time, only 2 programs can run. And the job of your OS is to make sure it runs those 5 programs in a way that you didn't even realize they are running 2 at a time. So a good OS should operate where the user never realizes that OS running. This is like a good system design. Good system should make sure that the user never realizes the system task exists. Everything should work from get-go. I just run a program, the program run correctly, done, right? So priority and privilege allow the OS to handle things like, okay, this print job is probably less important than whatever I'm trying to draw on my monitor when I'm playing games, right? The I/O, how do I deal with disk, network, and other things? Threat management, power management. I'm turning off my, well, not now, but like usually it's by default turning on my screen, right? When I'm turning on my screen, should I throttle? Should I make the CPU run slower? Because I mean, nothing is running right now, right? Why do I do that? Save power. ISA has a way to, like, for your program to save power. Should you make CPU slower? You can run a command to tell, hey, go slower. You don't need to go that fast. Save energy. The most important bullet point of it all, don't have to memorize all of this. Why? Each ISA has a big manual that I don't want you to memorize. You just need to know how it works. Then if you need to actually work with that, go check the manual. It's too big to memorize. Just need to know how to actually process. All right. So instruction is basically the most basic element that interface between your software and hardware, right? Now, if you zoom it in, it has 2 components. Again, the verb and the subject. Opcode, what does the instruction do? The operand. The operand are the who have to perform the instruction. For example, if I want to write a really stupid dummy instruction that says add R0, R1, R2, these are register. Think of it as a temp variable. In this case, let's say it means that I want to add R1 and R2 together, write the result to R0. Let's just assume that's the case. Right now, I'm just using this dummy instruction because we're not going into x86 or the x86 assembly yet. All right. In this case, R1, R2, R0 are the operand. And the operator is the plus, the addition. Now you see the register. Basically, the purpose of having registers is because they are fast, they are temp storage that the processor can directly access and use. When you want to do some operation like add, subtract, multiply, in modern processor, you have to take the data, like each, again, when you write code in C, everything has an address. The address is the location in my DRAM, in the memory. To actually add, say, 2 variables together, you have to get the data from that address in DRAM, put that in the register. So the first thing you do, put that in the register, then you add them together. The register are visible to programmer. These are something you can work with. If you want to program in assembly, you can work with register. I've heard story for anyone seen the game cassette back in the Famicom, like cassette, like Mario 1, like the old version of Mario? Yeah, something like that, right? The physical cassette that you plug into the machine. Those are actually inside the cassette. Anyone actually break them? I don't want to say that, but like anyone try to break them apart and see what's inside? Yeah, it's just a board with a chip, right? It's a board that has multiple chips in them. Inside the chip, they are actually, some of them are memory that store the game. It's actually have a chip that store the game, and when you plug it in, your machine reads the memory that has the game inside so you can play on it. That's how it's done. Now, back in the day, people actually, let's say you want to have a fancy game, right? If you want to have a fancy game, it means that you need a lot more for your program. You need to have a long program, for example, right? So people actually go and hack assembly code to make sure you fit, like everything fit within this much memory. So I've heard story of game developers actually go and look at assembly code and see how do I optimize this so it fit within one cassette and not multiple cassettes. Right? Nowadays you don't have to do that, but registers are visible and programmer can use this to further optimize the program. Another good example, for example, here, right? This is the board and it runs some program, something simple, but it should have enough code here that allow me to switch from the HDMI to video, right? For my projector, I can then switch and use a different color setup and all these things, right? I need to make sure the program fits in here. Compute instruction can directly access this register, add, subtract, multiply, and a group of register, we call this the register file. The CPU will have one register file, which is basically a bunch of register inside, right? And if you compare this to the memory, register is really fast. Within one cycle, one clock cycle, you should be able to read the data from the register. If you look at the memory, you're looking at like 30 to 100 to 200 or even 1000 clock cycle, depending on how the program are running at the moment. But they are a lot slower. That's why when you want to run your program, most of the time the data that you have to access will be put inside the register to run. Great question. They're not free. Actually, they're not being free. It's just getting overwritten. There's no need to free them, basically. By the time you're at assembly language, everyone assumes you know what you're doing or don't program in assembly. And my recommendation, unless you really, really, really need it in your entire career, you don't have to use this. Our community, like a computer science community, move further along enough that you can do everything in the high level language, which is a good thing. All right, now the last thing is a special register. Why are they special? Let me ask this one question. If that program are in the memory, it means that when I run a program, my computer need to know what line I am at. Why do I need to know what line I am currently at? So I can go to the next line when I'm done, right? The way you run a program is line by line by line. So you need to know what line am I at right now, so I know I can go to the next line. So I know I can go to the next line. The information is stored in the program counter. Again, because your program that you're running is in the memory, the only thing I have to store is the pointer to that line. Because that line is in the memory, it means it has the address. The program counter stores the address of the current line of your program that you're running. Typically, you would, yes. Basically, inside the program counter, to tell what line are you right now in the program when you run a program. Let's say you run a main function, right? You're done with the first line. You're now on the second line. The first line has an address. The second line has an address as well. The program counter stores those addresses. Whatever address it's storing right now, it tells both the programmer and the hardware saying, that's where I am. Yeah. How does it work for you? Does it have to go up the line? Great question. Then you basically change the program counter to go back. Because again, these are accessible by your assembly code. So there will be a line in assembly that makes sure the program counter takes the beginning of the loop. So it can jump back. And we do that using what I told earlier, the control flow instruction. If this is true, go here. If this is not true, go to the next line. Yeah. Typically, as I said, typically the program counter would get increment to the next line, essentially. Every cycle, go to the next line, go to the next line, unless you have if else or for loop. Oh, sorry. Then when you fetch the information, the instruction, there's another special register. So that program counter store the address. Instruction register store the actual assembly. So when you fetch, right, it's just ones and zero. That instruction is stored in the IR. So now you know what to do. You read the IR to know what to do. You read the program counter to know where you are in the code that you are running. Now, I would transition from C to x86, which is basically the majority of module number 3. So this is what happens when you run GCC, right? GCC translates your program into the computer language or assembly, right? So let's take a look at something simple. Here is the code. What does the code do? Assign A to 0, B to 5, add them, done. All right. It's a really simple program. By the way, should I turn off the lights? Okay. Now you can use the command once you have the code up. You can use the command gcc to compile into the .o. Then you can do obj dump -s on that file to get this. This is the object code in assembly that represent that program, right? This is your register. This is the address of main. So if you go to address 5FA, you will see the first line in the main function. This is the address of the first line, address of the second line, address of the third line. This is what goes into that first line. That's the command. The ones and zero that represent this instruction. All right. So let's take a quick break here because the next set of slides will explain what the heck is going on here. All right. We do some breakdown into what is this to the left, what are the things in the middle, what are the things to the right. All right. Now just be aware that that's a program you're running. That's all. Okay. So let me pause here quickly. After the maybe 5 to 10 minutes break, we'll resume. Here, now we have the assembly, right?
There's a question of midterm?
No. It was not yours. Not yours. Yeah. This class used to be a junior year, like the third year class. So they would cover more things on the side. It actually assumed you take the soup already. So back then.
Why is it not after the first year now?
Oh, the material changed, right? It used to be like we cover when we go through like the pointer topic, we go to like multiple data structure, we go to tree, to implement the tree here. It basically the decision becomes let's make sure you guys know C early. If you want to go to like system side of things, you can do it early. And that helps a lot actually. So that's why we have this break into like, okay, you take this class, then you take DSoup, and if you really want to, you can implement those things you learn in DSoup in C. All right. So with the code example here, right, I showed you already 5FA is where your main function is located in the memory. If you go there, you'll find your main function. Now here, the left side, 5FA, 5FB, 5FE, these are the location of each line. When you go to address 5FA, you see the first line. When you go to 5FB, you see the second line. You go to 5FE, it's the third line. Now my question is, 5FA to 5FB is jump by 1, right? 5FB to 5FE is jump by 3. Why is that the case? It has to do with the guy in the middle here. The middle guy is the actual binary that corresponds to the instructions. Basically, 55 here translate to the command that the computer knows. The computer will read in and say, oh, 55, okay, what I have to do is to do this, push RBP. And 55 in hexadecimal is how many bytes? 1 byte. 55 is 2-digit. Hexadecimal is 0 to 255. That's 1 byte. 2-digit in hexadecimal is 8 bits. In binary, that's 1 byte. Okay. That's why the first command is, because it only is 1 byte long, right? If the first command starts at 5FA for the address, where is the second command? 5FA plus 1. Because my command is only 1 byte long. I was at 5FA and it's only take 1 byte long. The next command is going to be 5FA plus 1, which is what? 5FB. So now the next command is for H89E5. And it just happened to correspond to this particular assembly code, move RSP RBP. I will not talk about what does RSP mean, what does RBP means yet. Just imagine those are some instructions that you can see and the computer know what to do. Basically, when you see for H89E5, it knows exactly what to do. And because these are 3 bytes long, for 8 is 1 byte, 89 is another byte, E5 is another byte, so it's 3 bytes in total. The command start at 5FB, right? 5FB, you have 3 bytes, 1, 2, 3. So from 5FB, you add 3 to that. So you ended up, the next line will start at 5FE. Then the next line, because it's, how many bytes does it take? 7, right? It's 7 bytes. So when you finish this line, the next line is going to start at 5FE plus 7, which is 605. And you can keep doing this, right? Now you know how to tell the location, and you know how big each line is, right? Then you can tell, okay, where's my next line? Your program counter will start from 5FA, then go to 5FB, then go to 5FE, then go to 605, then 60C, then 60F. So that's where the actual bits that correspond to the assembly that you command the computer to do.
What value does it take from the instruction to?
Oh, to increase the program counter, you mean? So that's done internally in the hardware. So the programmer doesn't have to worry about that. It knows, like the hardware design will make sure that it knows, in this case, go by 1 byte, this case go by 3 bytes, this case go by 4 bytes or 6 bytes or 7 bytes. So the hardware implementation need to follow that. Now here, as you can see, add, EDX, EAX, these are the, oh, not the actual, sorry about this typo. These are the actual assembly instructions that say, I want to add the 2 values here, EDX and EAX, and then write it back to EDX. That's how 86 works. We'll go into that next, this Thursday in the next lecture. You go into that and see what does the instruction mean. But the right side here is just the instruction. The right side is add, right? The left side 0, 1, D0. These would basically correspond to add, EDX, EAX. Now, you saw the sample of instruction, right? And as I said, there are 3 types of instruction. The first type is called compute. This performs the actual computation. You have memory instruction that has to move data in and out of the memory into the register or the register back to the memory. Then you have the control instruction that determine where is the next line. By default, literally go to the next line. But if we have control instruction, you can use that to implement if else or for loop. Jump somewhere, jump totally in the totally different places. So here, right, these, when I said opcode, this push, move, all these things are opcodes. It tells, it's the word part, the opcode itself that the computer sees will be somewhere in here. If you list out 5, 5 is basically 0, 1, 0, 1, 0, 1, 0, 1. In there will be some bits that the ISA will say, hey, that's the opcode. If you see, for example, 0, 1, 0, 1, 0, 1, that's a push. I actually forgot what's the opcode for a push, so I might be wrong. But basically, if you look at 55 as the binary, some of them will correspond to, if you see this pattern, that's a push. If you see this pattern, that's an add. If you see this pattern, that's a move instruction. So that's the opcode. And that part goes to the overrand. So there'll be some parts in your binary, the binary that correspond to the overrand. It will tell you what register are you dealing with. Are you adding this guy with this guy, or are you adding this different register with another register? How do you take the value? This, when you see $sign in your assembly code, $sign represent the value. $sign represent the value that you want as a constant. You can also have the value that go in as a part of the address. For example, how many people see like pointer? I can do something like this, right? I have P as a pointer, and then I do P plus 1, and then the reference. I start with P and then I add 1 to that. I want to go to that address, not this guy. Same thing here. I can have the pointer and then I put some constant that I jump like 1, 2, or 3 or more. We'll go into more detail here. So that's the base for the register that involved with the address for that instruction. Now to move the program counter, if you start here 5FA, as I said, it's only 1 byte. So the next line is going to be at 5FB. The next line program counter will be at 5FE, and so on and so forth until you reach here. At the end, there will be enough information, enough binary for the program to say, hey, that's the end of my program. Go back. You're done. In this case, it's a return. Return Q means that return from the main function. So whoever called the main function, which is basically your shell, for example, that called the main function, that's it, you're done. Here's the return value. All right. So in the next 3 classes, we will break down assembly to the right. What does push mean? What does move mean? What does add mean? Then we'll go into if I have if else. How do I implement if else in assembly? If I have for loop, how do I do that? And we'll end with when I have a function call, because I mean, in your program, one of the most important things is handling function call, right? How is that handled in assembly, and how does it look like when the computer actually processes it? All right. So actually, that's it for today's lecture. I want to use the remainder of your time because we just had an exam. There's no in-class, but assignment 3 Q&A because it's a lot of things. Okay, so how many people start assignment 3 yet? Good. Ask me questions. All right. That's it for the class today. We'll see you guys for the lecture part. We'll see each other on Thursday. I'll be here in the room. I'll also look at WebEx chat if you have any question on assignment 3. All right.